Hello, welcome back. We're solving more trig equations. In this equation, I notice now that I have two different trig functions in the same equation. We have cosine theta, goes on both sides, and then we have a cotangent theta. Okay, so if you think of this as an algebraic equation, if I use a different variable for each trig function, I'll say y be cotangent theta, and I'll let cosine theta be x. So my equation is x times y equals negative x. Now, I don't know if that helps, but if you think about how you would solve an equation like that, many students want to divide both sides by x, which we can't do because x is a variable. Okay, if it was a constant, we could do that. But when it's a variable, we have to be careful because depending upon what x is, what type of equation it is, if we're solving, we could end up losing a solution. So if we go back to our rules, if we follow these rules, it'll catch us from doing something like dividing both sides by cosine theta. So decide whether it's linear or quadratic. We would say that this is linear because all my trig functions are the first power. If only one trig function is present, that's not our case. We have more than one. So here's where we are right here. If more than one trig function is present, rewrite the equation so that one side equals 0. So we want to get everything on one side equal to 0. All right, which means we are going to add cosine theta to both sides, or basically move it over to the other side by adding the opposite. So that means I have cosine theta, cotangent theta, plus cosine theta equals 0. Okay, because when I add it over on the right, it's gone. So then I have to add it to the left. All right, so after I make it everything on everything equal to 0, then we try to factor if possible. All right, well, I have two terms. This is a term and this is a term. First factoring method you should always try is greatest common factor. Do not forget that. Greatest common factor is our friend. Okay, so I can see that both of these terms have a factor of cosine theta. So I'm going to factor that out, which just means divide. So I'm dividing out a cosine theta, so I have cotangent theta plus 1 equals 0. And then remember after we factor, we said each factor equal to 0. That's that 0 product property. So we're saying okay, what's the value of theta that when I take its cosine, I get 0. And what's the value of theta that when I take its cotangent and add 1, I get 0. Okay. One thing I wanted you to notice is that look what happens when we factored. I have my trig functions occur in different factors. Cosine is in this factor, and cotangent is in this factor. So then we end up with linear factors, and then when we set them equal to 0, we have linear equations that we know how to solve. So here, my trig function is already isolated, so all I have to do is come up with the angles. Let's solve this in radians. And how about if we just say, let's solve on the interval from 0 to 2 pi. I think we know how to add the integer multiple idea to get all solutions. Okay, we've done that. Oops, come on, come over here. All right. So, all right, so what are we looking for? We're looking for angles whose cosine is 0. Well, cosine is 0 when we are at pi over 2, and 3 pi over 2. All right. So pi over 2 and 3 pi over 2 are angles that make that factor equal to 0. So there's 2 of my solutions. And then over here, this is a linear equation, so we need to isolate cotangent theta and then figure out what that angle is. So cotangent theta is equal to -1. Now, if you're okay with cotangent, totally fine. If you want to rewrite that as tangent, that's fine also if we know tangent a little bit better. We could say, okay, what's the angle whose tangent is the reciprocal of -1, which happens to be -1. So let's think about angles whose tangent is 1 or -1. Those are our pi over 4 multiples. So we are talking tangent is negative in quadrant 3 and quadrant 2 and quadrant 4. All right, so the angle in quadrant 2, whose tangent is -1, would be 3 pi over 4. And in quadrant 4, the angle would be 7 pi over 4. So if I was giving my solution set, my theta would be the angles pi over 2, 3 pi over 2, 3 pi over 4, 7 pi over 4. So we could always go back, or we should, I would say, go back and test each angle back into the original equation. Okay? But these are all angles in the interval from 0 to 2 pi. All right, let's look at a different one. Now we got something else going on here. Notice how this equation is already set equal to 0, but there's 2 things I should notice here. First of all, I have 2 different trig functions. I have cosine and I have sine. The other big difference is that I'm mixing multiple angles, double angles, and single angles. So, for example, this is 2 theta and this is 1 theta. Okay? That's like apples and oranges. We can't mix those. Okay, so I need my equation to have all the angles as either 2 theta or all the angles as 1 theta. So I think it's probably best to go to 1 theta or single theta because I know I have an identity for cosine 2 theta. Now, there are 3 of them, so I have to choose which one do I want. There's one that has both sine and cosine. There's one that has only cosine and one that has only sine. Since this other trig function is sine, then I can take care of 2 problems in one. I can get rid of the double angle and I can turn cosine into sine by choosing the double angle identity involving only sine, which is 1 minus 2 sine squared theta. All right, so if I do that substitution, now look what happened. Only sines and only single thetas. All right, so I now can see that it is quadratic because of the squared. Everything's on one side equal to 0, so it's quadratic, so I'm going to put it in descending order. equal to 0, and then I'm going to try to factor. If I can't factor, I'll use quadratic formula. So now it's just basic algebra, doing some rearranging. So I have a 1 and a negative 2 that I'll combine. Here, let's do this first. Negative 2 sine squared theta plus 3 sine theta. Combine my constants. 1 minus 2 is negative 1. Okay. Now, when I factor or use quadratic formula, I don't really like the leading term to be negative. So I'm going to go ahead and multiply both sides by negative 1 or divide both sides by negative 1, change the signs. So I've got 2 sine squared theta minus 3 sine theta plus 1 equals 0. And now I'm going to factor. This has a leading coefficient of 2, so whatever method you use, if you use the AC grouping method, trial and error, whatever method you can use to come up with it. But it does factor into 2 binomials, and it is factored into 2 sine theta minus 1 and sine theta minus 1. Once I get it factored, I notice now that these are linear factors. I set each linear factor equal to 0, and I'm solving 2 linear equations, linear trig equations, which we've had a lot of practice. Isolate the trig function in each situation and then figure out the appropriate angle. All right, so here I get sine theta equals 1/2, and here I get sine theta equals 1. So now I have to figure out the angles between 0 and 2 pi that have those values of sine. So 1/2, sine is 1/2, we're talking pi over 6s, and sine is 1. We're talking basically positive 1 is going to be pi over 2. So 1/2 sine is positive in quadrant 1 and 2, so it'd be pi over 6 and 5 pi over 6. So I've got my angles between 0 and 2 pi. So theta is pi over 6 in quadrant 1 and 5 pi over 6 in quadrant 2. And sine is 1 at pi over 2. So our solution set would be those 3 angles if we're talking between 0 and 2 pi. Now we can check those back into the original equation. Okay, one more. Once again, 2 different trig functions, cotangent, cosecant. All right, so I need to get them to be the same. I can do that first, or I can make that equation equal to 0 first. It doesn't matter. I think I'll make it equal to 0 first, and then I'll do my substitution. So cotangent theta plus 4 cosecant theta plus 5 equals 0. Right? So I'm thinking cotangent theta, I've got a Pythagorean identity that involves cotangent theta. And what is that identity? It is cotangent squared theta plus 1 equals cosecant squared theta. So if I want cotangent squared theta by itself so I can replace that, then I need to subtract 1. So I have cotangent squared theta would be equal to cosecant squared theta minus 1. So where I see cotangent squared, I can now replace it with cosecant squared theta minus 1. So I can do a substitution here. Alright, so I've got cosecant squared theta. Oh, why that eraser is there? Decides to make me crazy. So I've done my substitution, and now once again I can see one trig function, it's quadratic, put it in descending order, combine like terms, and then either factor or use quadratic formula. So we end up with cosecant squared theta plus 4 cosecant theta. Negative 1 positive 5 is 4. Okay. If you notice, this is actually a perfect square trinomial, but if you don't, you can factor. So we're looking for numbers that multiply to be 4, add up to be 4, which would be 2 and 2. So since I have the same factor, I really only have to set one of them equal to 0 to find my solution. So cosecant theta is negative 2. Cosecant is the reciprocal of sine, so if the cosecant is negative 2, the sine is negative 1/2. So I'm looking for angles between 0 and 2 pi, whose sine is negative 1/2. So sine is negative in quadrants 3 and 4. That's 1/2. It's a pi over 6 multiple. So theta would be in quadrant 3 would be 7 pi over 6, and in quadrant 4 would be 11 pi over 6. So those are my two solutions between 0 and 2 pi. And that's it. More equations to come in the next video. Stay tuned.